Okay, testing this. Welcome to my attempt at recording videos where I show you how to solve the questions from the end of year mock exam tests that we had just before the summer break. I've divided the videos into 6 parts. That is 3 parts for paper 1 and 3 for paper 2, where I start the first round taking this, what I consider the easiest marks. And then second round is like the medium marks, and then the last round is the hardest marks for both papers. So this is the first video, and I am attacking paper 1, and I've chosen 6 questions, like 1, 2, 3, 4, 7, and 10, which I consider to be the easiest ones, and they mount to around 37 marks, which is a solid grade 3. So these are the stuff that all of you should feel that you can just do more or less mindlessly and very, very fast. Especially the first questions, you'll notice that you have very little time to do these. So they need to be kind of automatic. Let me try and show you how to do it. So if we roll up, it's going a little bit slowly, and there we are. Question 1. In this question, it's a 5-mark question, so we have around 5 minutes. We're given 2 functions, f and g. And in the expression for g of x, we have this constant k that we don't know the value of yet. In any case, question A asks us to write down an expression for, and this is really just reading comprehension. So you need to be super familiar reading this, that it's what we call g after f of x. So the composite function where we start using the function f and take the result of that and put into the function g. So what we do for that is that saying that g after f of x means the same as taking g of f of x, and we can say that's taking g of, and then we can just read what's f of x, that's x minus 3, and then we put that into the function g. And what g does is taking whatever we put in, x, and square it, so it becomes x minus 3 squared, and then adding k squared. So it looks like this, and that's the result. And for question B, we are given that this g of g after f, if we take it at 2 instead of x, then the result was 10. That's information for us. And we're being told to now find the possible values of k. So we really just need to write down the information we're given. So g after f, we just found an expression for it. Now x is 2, so when we could write g after f of 2, then it just means that we plug in 2 in the expression above. So that's 2 minus 3 squared plus k squared. And we can simplify a bit because 2 minus 3 is just minus 1 and squared is just 1. So this is just 1 plus k squared. And the information is that this is 10. And hooray, that's an equation about k. And if we want to solve for k, then we subtract 1, of course. So k squared is 9. And we have to be a bit careful taking the square root, remembering that there are 2 solutions. So k is either plus or minus the square root of 9, which is plus or minus 3. And those are the possible values. Onwards to question 2. In this question, we are talking probability theory. We have 2 events called A and B, and they are such that the probability of A is 0.65, probability of B is 0.75, and the probability of their, again, this is reading comprehension, their intersection is 0.6. So what I do when I get this information is that I immediately draw a Venn diagram. So what we're being told is that we have A and B, and the intersection lies in here. That is probability of 0.6. It's a bit hard to put in the rest of the information because you can't really draw P of A because it includes the intersection. But we can already kind of mentally subtract and say, well, if all of this is 0.65 and we have 0.6 in here, then this is 0.05, what's left. And same goes for the other one. If all of this is 0.75 and we already have 0.6 in here, so then we have 0.15 left for this. But they're asking is to find the probability of the union, A union B. And if we already did this thinking work up here, we can really just add up. I'm just going to do that. So we're adding, we get something like 0.2, which we add to 0.6. So that's 0.6 plus 0.05 plus 0.15, which is 0.8. And that's the probability of the union. You could also, if you look up in your formula booklet, say that the probability of a union is always equal to the probability of one plus the probability of the other, except then you've counted the intersection twice, so you need to subtract the probability of the intersection. That's going to give you the same result. In any case, that's just, if you like, using formulas rather than thinking. Question B says, hence or otherwise find the probability of, and here we have to be very careful with the reading, probability of the complement of A intersected with the complement of B. And the complement of A is everything that lies outside of A. So the stuff that lies out here on my drawing, it needs to update. There goes. But including the stuff that lies in B but outside A, but then if we intersect that with the complement of B, then what we really get is everything around here. And in fact, that's a general rule that the intersection of the two complements is actually the same as the complement of the union. So if you, again, like formulas, then kind of this is the way to attack it. Because how do you calculate the probability of the complement of anything? Well, that is 1 minus the probability of whatever you took the complement of. So 1 minus the probability that we just calculated. That's why they write hence, because then we can use the stuff that we just calculated. So this is 1 minus 0.8, which is 0.2, and we're done. Moving on, whenever my hardware gets ready, to question 3. In this case, we have the sum of the first n terms of an arithmetic sequence is given by this expression. So the hard thing here, this is a little bit more tricky. The hard thing here is this is quite unusual, that we get a formula to calculate the sum of the first n terms. So it's kind of starting off the wrong leg, but it turns out to be surprisingly easy. So let's just attack it. Where we know that P and Q are some positive constants, then we're given the information that S4 is 40 and S5 is 65. And how do you just connect these? Well, the thing is that 40 is equal to S4, and we just had a way of calculating S4 because it's right up there. This is P times 4 squared minus Q times the n, that is 4. So this is 16P minus 4Q. And this starts looking really nice because we are out to find the value of P and Q. We have one more information, which is that 65 is equal to S5, which is equal to P times 5 squared minus Q times 5. So that's 25P minus 5Q. And we're not done, but this starts looking really nice because we have two equations that are simultaneous equations about P and Q. So if we know how to solve these guys, then we are kind of done. And can we do that? Yes, we can. So one way of attacking it is to realize that if we multiply the first one by 5, then we get something like 5 times 40, that is 200, is equal to 5 times 16, that's 80, times P minus 20q. And if we multiply the other one by 4, then it starts looking really nice. So I'm just going to do that. 4 times 65, that's 260, is equal to 100p minus, again, I get 20q. So what do? I'm going to subtract these two equations. I'm going to take the top one and subtract from the lower one. So what do I get? I get that 60, that's the difference, is equal to 20p. And the nice thing is that everything else cancels out. So to get p, we just take 60 and divide by 2, 20, or 6 divided by 2, so p is 3. And then, of course, we can just say that we can go to the first equation and say now 40 is still equal to 16 times p, which is now 30 plus 18, that's 48, minus 4 times q. And then we get that minus 8 is equal to minus 4q, so q is 2. And there we go. Now, we have very little space for question B, and we start getting worried, but we realize that what they ask for in question B is the value of u5. So u5 is actually the term in the sequence that we've hardly even addressed yet. We've just worked with the expression for the sum. But now we have to talk about the sequence. And how do you do that? Well, if we realize that what the sum actually does, and kind of think we have very little, we only have 2 minutes to do this, and what is the work we just did? Well, the thing is that the question we just worked with gave us the value of this S5 sum and the S4 sum. And the S5 sum is the sum of the first 5 terms. And the S4 sum is the sum of the first 4 terms. What do you get when you subtract those from each other? Well, you get only the 5th term. So the 5th term can be calculated as taking S5 minus S4, which is 65 minus 40, which is 15. And we're done. Or wait up, I just did one of the things you do when you work really fast. If you take 65 and you subtract 40, you don't get 15, you actually get 25. And now we're done. Moving on to question 4. Is type of question that looks kind of scary when you don't have your calculator, because you quickly end up with having to calculate inverse cosines and stuff. So on paper 1, this stuff is scary, but usually it's manageable. So we have a triangle ABC, and we get a side length AB and another side length that is AC. And we get the information that the cosine of the angle that lies in here is 1 over 5, and we have to find the area of the triangle. So the cool part, or the cool thing to be thinking here, is that we almost know this angle. We have the cosine of that angle, and we have 2 sides. So 2 sides and the angle between them, how is that related to the area of the triangle? Well, it's related like this. The area is 1/2 times one side length, which is the square root of 6, times the other side length, that is 10, times, but then we need the sine of the angle between them. And we're kind of not so happy about that because we only know the cosine, but then we realize that, hey, the cosine and the sine, they're completely related. We just need to know that the sine of A squared plus the cosine of A squared, which is 1 over 25, equals 1. So if we subtract that on both sides, we get that sine of A squared is 1 minus 1 over 25, which is 24 over 25. And then we take a square root, get that sine of A is either plus or minus the square root of 24 over 25, which is plus or minus square root of 24 over 5. Again, that's the sort of shit you don't really want to happen at paper 1, because it looks pretty awful. You can start out by realizing that this plus minus, in this case, we can ignore it because the sine of the angle A is going to be positive when A is an angle in a triangle because it's going to be smaller than 180 degrees. So we ignore this because we're doing trigonometry, and we can really just try and attack it. So we have the area above, and this then becomes 1/2 times the square root of 6 times 10 times the square root of 24 over 5. And now really nice things start happening because, first of all, this 1/2 times 10 is 5 and we divide by 5, so all the integers disappear. What we're left with is really just the square root of 6 times the square root of 24, which you can do by just multiplying the two interiors of the square roots. So it's the square root of 6 times 24, which happens to be the square root of 144. And then we get this really nice experience that actually this square root is super nice. It's equal to 12. And that's sort of the feeling that we might actually have done something right in a paper 1 situation. So moving on, we're skipping question 5 and 6 for now and attacking question 7, where it's it's about complex numbers. So we're given that this number z is equal to 5 plus qi and satisfies an equation that is z squared plus iz is equal to minus p plus 25i, where p and q are unknown real numbers. We have to find the value of p and q. So how do we do that? Well, we need to realize that we have to involve this expression for z in this equation that is talking about z. So there is no way around just substituting what z is into the equation. So what do we get? We get 5 plus qi, which is z, has to be squared plus I times z, that is again 5 plus qi, which is equal to minus p plus 25i. And it's not really a standard situation that we've been in hundreds of times before, but we can kind of imagine doing something about it because we can calculate with complex numbers. So let's open this square, for instance. We get 25 and we had qi squared, then the I squared becomes minus 1, so we actually get minus q squared, and then the double product becomes plus 2 times 5 is 10 times q times I. That's for the first guy. The second guy gives us some 5i. We multiply I into the bracket, and then we get I multiplied with I gives us minus 1, so we just get minus q, and that's equal to minus p plus 25i. And we're kind of a little bit worried because this is just one single equation, and we don't really have any other information anywhere, and we still have both p and q being unknown. But nice things are about to happen, because when are two complex numbers the same? It's when their real part are the same and their imaginary parts are the same. So if we start tidying up the left-hand side, for instance, if we take the real part for itself, we get 25 minus q squared minus q. That's the stuff that has nothing to do with I. We could put a bracket around it. And then the I stuff, the imaginary stuff, is plus 10q plus 5 times I. And that's equal to minus p plus 25i. And the right-hand side is just a real part plus an imaginary part times I. So when are these the same? Well, it's when the 25 minus q squared minus q is equal to minus p, which is kind of complicated. But then the nice part is that 10q plus 5 has to be equal to 25. So obviously, the nicest of these two equations is the last one. If we take that one, we get that 10q is 20, so q is 2. And that makes the first equation much nicer. So going to this one, we put in q being equal to 2, it says that 25 minus 4 minus another 2 is minus p. So what's that? That 19 is equal to minus p, so p is 19. And we're done. Except for this last step, again being one of those things you do when you work really fast. If minus p is 19, then p is not 19, it's minus 19. The final question in this first round, we skip 8 and 9 for now, is surprisingly question 10. This is in section B, where you're actually supposed to work in your answer booklet and writing the answers there, as it says very clearly up here. But since I'm working in this tablet, I can't have an answer booklet next to, so I'll just write my answers here. Please pretend that I'm writing in the answer booklet. Section B questions are much longer, which you can also see that this is a 15-mark question, so you're supposed to spend some time on it. But this question, even though it looks long and scary, it's surprisingly easy. It's actually a 2-page question because it's going to continue on the following page. But let's just dive into it. We have functions f and g defined by 2 different expressions, where, yeah, they're right there. So question A tells us to state the equation of the vertical asymptote to the graph of y equals g of x. So it's about this guy. What do we need to do? We need to think, vertical asymptotes, they are the ones that go vertically. When do they happen? They happen at values of x, they're vertical, so they stand in values of x, where the function is not defined. So we look at the function and say, well, is there anywhere, it's only defined for x being larger than 0. Is there anywhere for x being larger than 0 where this expression here doesn't make sense? And d is a positive number, so that's not really the case. So the graph lies on the right-hand side of the coordinate system, and it's defined everywhere. So where could the vertical asymptote be? Well, the answer is that if we were to draw the graph of this guy, the only place that we could sort of approach with values of x where the function is not defined is x being 0. So the answer is really just, it's when x is 0. If you were looking at the graph of the function, for instance, if you had your calculator, this would make a lot of sense. But the logic here is really just to say, well, what's a value of x where the function is not defined that we can sort of approach through values of x where the function is defined? And the only possibility is really x being 0. So that's the guy. Moving on, the graphs of f and g intersect at 2 distinct points. Then we need to think, when do the graphs intersect? It's when the 2 functions give the same function value for some value of x. So kind of even before we start in question B, we want to focus that this happens when f of x equals g of x. And if we take the functions f of x, that's ln of 2x minus 9, and the other function g of x is 2 times ln of x minus ln of d. Well, that's the equation that we need to solve in order to find the values of x where the graphs intersect. Now, question D says that we have to show that the points of intersection, at the points of intersection, the values of x fulfill this equation. And that's not really the same because there are no ln's in this equation. So we kind of need to think, how do we get rid of those? One thing that we can start by thinking is that having 2 logarithms, well, first of all, having a number 2 multiplied on a logarithm is the same as putting the 2 inside the logarithm as an exponent. So we can do this. And second, if you have 2 logarithms subtracted, that's actually the same as having a fraction inside the logarithms. So x squared over d. And this is really nice because when our 2 logarithm values the same, it's only when the interior are the same. So this equation is really the same as 2x minus 9 being equal to x squared over d. And if we multiply d on both sides, then we get, take the right-hand side first, x squared is equal to 2 times d times x minus 9 times d. And, well, we need to move these two terms to the other side of the equation, and we get exactly what they are suggesting. So that's for part 1. For part 2, we need to now show that, again, there's this hence, show that d squared minus 9d must be larger than 0. And we have to sort of recall that the information we were given is that the graphs, they intersect at 2 distinct points. And we get this equation describing which values of x those points can be. So we kind of need to think, this equation must have 2 distinct solutions. And looking again at the equation, it's clearly a quadratic equation. So putting those pieces together, it's really about saying, well, the equation must have a discriminant that is larger than 0, which looks really nice because we need to show that something is really larger than 0. So for 2, the idea is to just say, well, let's calculate the discriminant of this guy. Let's just take it in the form that it says up here. The discriminant is the coefficient of x, which is minus 2d squared, and then minus 4 times the constant coefficient, 9d, times the coefficient of x squared, which is just 1. And this must be larger than 0. And if we simplify this, then we get 4d squared from the first one minus 36d from the second one is larger than 0, which is kind of what we wanted, except that we can divide with 4 on both sides. And we can do that on an inequality, because inequalities you are allowed to multiply and divide with positive numbers. So dividing with 4, we get that d squared minus 9d is also larger than 0. And we're done with 2. Finally, we have to find the range of positive values of d. So now we kind of need to switch mode inside the head and saying, well, we just found out what the possible values of d are. They're the ones that fulfill this equation. That's a new, or it's not an equation, it's an inequality. That's a new quadratic thing, because this is a quadratic expression in d. And how do you solve quadratic inequalities? Well, you turn them into quadratic equations first. So what we need to do is to think, well, let's start and find out when this is actually equal to 0. So that's d squared minus 9d being equal to 0. And that's kind of the easiest quadratic equation in the world, because either d is 0 or d is 9. You can sort of see that instantly. So that's when d is equal to 0 and d is equal to 9. And then for the rest, that's when we have equality with 0. So in order to kind of solve the inequality, you need to think graphically. So it's a good idea to kind of visualize that you have a sort of coordinate system where the x values are actually values of d. And what depends on d? Well, it's the value of the discriminant. And we just found out that when d is 0 and when d is 9, we get a discriminant that is equal to 0. And we want it to be positive, larger than 0. Then we just look at this function expression here again. And clearly, since the coefficient of d squared is plus 1, then we know that the parabola, that is the graph of this function of d, is concave up. So we can kind of sketch the parabola up here. It looks like this. And we can clearly see which values of d gives us a positive discriminant. They are the ones where d is either larger than 9 or d being smaller than 0. But since all the way in the very beginning, we were being told that d is a positive real number, we can safely go and ignore the bit where d is smaller than 0. So the actual answer to the question becomes d must be larger than 9. Finally, it's very important to not just stop here and celebrate, because the question continues on the following page. So we skip the page. And the follow-up shows us first what we kind of wanted in the beginning, namely the graphs of f and g, at least one example of how they can look for a particular value of the constant d. And in this case, we have a picture where the graphs intersect when x is equal to p and x is equal to q, and p being the smaller one of those. Now, they tell us that this is the case where d is equal to 10, and we notice happily that this matches with our result from before, that this is one of the values where d is larger than 9, so we actually do have two intersections. And what they tell us to find is the difference between q and p. And it has to be expressed in a certain form. So what do we do? Well, we have to find those values of x where they intersect. And if we remember from back here, it all came from this equation that we underlined up here. But now for the particular value where d is equal to 10. So we could sort of, this is very hard while I record, but we have to try and memorize that it's x squared minus 2dx plus 9d. So we write x squared, and I forgot, minus 2dx plus 9d equals 0. That was the equation, and we plug in d being 10, so it says x squared minus 20x plus 90 equals 0. And all we really need to do is solve this quadratic equation to find the values of p and q. So my favorite way of doing it is finishing the squares. So this is x minus half of 20, so 10 squared minus 100 plus 90 equals 0. So x minus 10 squared is minus, well, it becomes minus 10 here, so it becomes 10 on the other side. So what do we get? X minus 10 is plus or minus the square root of 10. So x is 10 plus or minus the square root of 10. And what we have is that, of course, the larger value q is where we take plus, and the smaller value is where we take minus. And what they wanted to calculate is the difference q minus p. So that's the plus version of this minus the minus version of this. We could write it and say 10 plus the square root of 10, and we subtract 10 minus the square root of 10. And what we get is that the 10s cancel out, and we have 10, the square root of 10, plus the square root of 10. So that's 2 times the square root of 10. And thankfully, that's exactly in the form they wanted. An integer a times the square root of another integer b, where both are positive. So that's the result. And we are done with this part. So what I would like you to notice in this last question is that I picked it as one of the easy ones. And since it's a section B question, it's kind of not that easy for the simple reason that it's very long, that it just keeps going and going. But if you really look carefully, you'll notice that every step along the way is kind of straightforward, the only thing you could think of doing. And it's for this one, it's mainly just solving quadratic equations all the time. So I took the liberty to include it among the easy ones. Now, hang on for part 2.